Please welcome our last guest in this year's Student Informatic Festival, Cormen.
Well, thank you. It is a real treat to be here, and I want to thank the conference organizers. They've done a superb job, especially Adam Pekarczyk, who has been my handler and has really helped me out. I was supposed to arrive here, yes. I was supposed to arrive here on Wednesday, but I'll show you in a minute why I didn't. But first I want to talk about the work that I'm going to tell you about. You can see that there's another name on here. It's Jessica Fan. So Jessica was my senior thesis student this year. She just graduated. She's class of 2017. She just graduated. Dartmouth is on a quarter system, and we just ended our winter quarter. Jessica graduated a term early, and the work I'm talking about is work that she and I did together, every bit of it. In fact, several of the results are hers and not mine. Really remarkable student, and I'm just so proud of the work that she did. So why did I arrive late? Well, this is my house, and this was my house on Wednesday morning after the snow cleared. Tuesday morning, there was no snow on the ground. So this is the storm that we got in New England, where I live, and I measured the snow in front of my house to be 36 centimeters, and the neighbor across the street told me he measured the same. He took this photo, and to clear the snow, this is what I do. So I have a little plow that I got this year, and I have a great time trying to figure out where to put all the snow. All right, so I'm going to talk about gray codes, and we're going to start off talking about a rotating shaft. So here's a shaft. It rotates in this direction, and we might want to know where in the rotation is it. For example, let's say we can divide up the rotation into 10 sectors, and we might want to know which sector of rotation are we in. And depending on which sector of rotation, we might want to actually have something happen. There might be some sort of actuator that causes something to happen. So one way that we can do this is we can put what's called a rotary encoder on the shaft. And the idea here is it's going to encode the 10 regions, and we're going to number them 0 to 9. We're going to number them in binary, and the green dots indicate sensors that go over this rotary encoder. And the green dots read whether they're over a white region or a black region. The white region will indicate a 0 in our binary number, and the black region will indicate a 1. So here's how we can look at it here. And we can see that the rotary encoder goes 0 to 9 in binary in order. And here the most significant bit is on the inner ring, and the least significant bit is on the outer ring. So let's see what happens as we are rotating our shaft and reading the rotary encoder. So we start out in state 0, right? 0, 0, 0 in binary. I think you know that probably indicates 0. And now we rotate 1/10 of the way around, and now we have the outer ring going from white to black. So now we're reading 0, 0, 0, 1. We're in state 1. We rotate a little bit more. We go to state 2. You guys good with binary? I hope so. And then we go to state 3, and then we go to state 4. And it would continue around. But I want to back up for a second. I want to back up to the situation as we're transitioning from state 3 to state 4. So here we are. We're just about to go from state 3 to state 4. We're at the very end of state 3. And you can see the sensors are still reading 0, 0, 1, 1. But what could happen is that as we transit from one sector to another, the sensors don't all read new colors at the same exact moment. So for example, we could get something like this, where the outer ring transits from black to white before any of the other sensors detect a change. So suddenly, we're not in state 3 or state 4. We're in state 2. We didn't want to be in state 2. And if there was something that was supposed to happen based on being in a particular state, the wrong thing is going to happen. And then we can go to state 0 as the next ring goes white. And then finally we get to state 4. But when we were going from state 3 to state 4, 2 bad things happened, which is we got to 2 wrong states. So that's not a good thing, right? we don't want this to happen. So let's see a different way to make this work. So here we're going to encode the states 0 to 9. And the idea here is that as we go from state to state, there is always going to be exactly one color change, from black to white or white to black. So with only one color change, we won't have these problems, what we call glitches. We won't have any glitches as we do that. So let's see how this really works. We start in state 0, and now we rotate, and we go to state 8. Now, granted, we're not going to go from 0 to 9 in order, but we are going to number these so that we always are changing just one bit at a time. So here, just the inner ring changes, and we go to state 8. Now the outer ring changes only, and we go to state 9. And then we go to state 1, state 3, and you can see it's always just one bit changing. State 7, state 5, 4, 6, 2, and back to 0. All right, so each time exactly one bit changed, and we're never going to have this problem of an actuator doing the wrong thing. So this is actually called a binary reflected gray code. It was named after Frank Gray, who patented it in 1953, working for Bell Labs. But actually, the idea behind a gray code has been known as late as, or I should say as early as 1878 by a mathematician named Émile Baudot. So let me show you how we make what's called the binary reflected gray code. What we see here on the left are the bits 0 and 1, and their decimal representations, which amazingly are 0 and 1. So as we go from 0 to 1, only one bit changes. It would be pretty hard to have more than one bit change when you have just one bit. So the way that we create the binary reflected gray code is that we take the previous gray code and we reflect it. And what we mean by reflecting it is we write it in reverse. So now we have 0, 1, and then 1, 0. And what we'll do is we will stick a 0 before the top half and stick a 1 before the bottom half. And you notice that as we go from one number to the next, exactly one bit changes. And I've also shown you the decimal representations of these numbers. And it's also true that not only do we have just one bit change as we go from one number to the next, but even when we wrap around, when we get to the bottom, 1, 0, and go back to the top, 0, 0, again, only one bit changes. We can repeat the process. Take what we had, reflect it, stick 0s in the top half, 1s in the bottom half. Now we've got the numbers 0 to 7 in some order. And we can keep going. Reflect the bottom half, stick 0s before the top half, 1s before the bottom half, and now we have the numbers 0 to 15 in some order. So that's what's called the binary reflected gray code. And the reason that I got interested in this in the first place is that I was doing work on fast Fourier transforms, and Jessica and I were working on this. And one of the subproblems that we had involved matrix vector multiplication over GF2. If you don't know what GF2 is, don't worry about it. But to do that efficiently, we had to figure out gray codes. And gray codes are great when you have things that are a power of 2. So let's talk about some of the gray code properties of interest. So we talk about the gray code property where as you go from one number to the next, exactly one bit changes. There's a property that Jessica and I called the density property, where what you have is a sequence that is the numbers 0 to n minus 1, but permuted in some way. So that's what you've already seen. So for example, the previous gray code I showed you was 0 to 16 minus 1. And the cyclic property, that's when you go to the last number, go back to the first, and still only one bit changes. And all of these properties hold for the binary reflected gray code, but the binary reflected gray code requires this n to be a power of 2. And usually in my life, I like powers of 2, but what Jessica and I were working on, we were thinking about what if n is not a power of 2. So let me give you an outline of the rest of the talk. We're going to talk about binary gray codes, and we're going to look at the binary reflected gray code a little bit more. And then we're going to look at dense binary gray codes where we have the gray code property, but n is not a power of 2. And the amazing thing to Jessica and me about that was that when we were wondering, how do you do a gray code? But that's a permutation of 0 to n minus 1, one bit changing, and n is not a power of 2. I mean, gray codes have been known for a long time, Nobody has ever asked this question before. It seemed like an obvious question to ask, and nobody had ever asked it before. We Googled around, we could not find it. And, I'm not that bad at Google. I may be old, but I'm not that bad. And, Jessica's young, so she should be able to do it. And couldn't find it. So we had to figure it out ourselves, and I'll talk about what we did. And then we wanted to figure out how to make these things cyclic. The solution that we found for dense binary gray codes, you'll see, is not necessarily cyclic. We wanted to figure out how to do that. And then we'll talk about fixed radix gray codes, where we have a number system that is not binary. For example, there's a fixed radix gray code, or a fixed radix system, I should say, that you're pretty familiar with, called base 10. But you can use any number base. And we'll look at a method by a fellow named Ayer for fixed radix gray codes, and then our solution. And then we'll look at mixed radix gray codes, where you can represent a number with several different bases for different digits. And we'll see how we came up with dense and cyclic gray codes for that. And then we'll see another question about cyclic gray codes for mixed radices. All right, so for the first part, binary gray code. So let's remember what the properties are here. So it has the gray code property. And the way to see that is you can see here, here are the places where just the rightmost bit changes, and then the next bit, and the next bit, and the next bit. So each time only one bit changes, and it's cyclic as we go from the last number to the first, just one bit changes, and it's dense, right? We actually hit all the numbers 0 to 15, no more, no less, no repeats, none of that. So it turns out that when Gray wrote his patent, he gave a formula to figure out, if given a position in the sequence, what we're calling an ordinal position, given a position in the sequence, how do you figure out what the gray code equivalent is? So if I ask you for the 18th position in the sequence, what would be the gray code? Well, Gray gave a formula for that. So here's an example. So x is going to be the index into the position, the ordinal. And here I'm going to use the number 11, the decimal number 11. And of course, the binary representation of that is 1011. And what Gray said is, well, what you need to do is XOR it bitwise with the number x over 2, take the floor. In other words, shift it right by 1 bit. So that's what I've done here. So 11, you divide it by 2, take the floor, you get 5. And you just do a bitwise XOR operation bit by bit, and you get the binary reflected gray code. Okay, so when we do that, we get 1110, which has the decimal representation 14. So Gray gave this formula. Now we're going to be talking about how to compute the ith bit of our gray code, given the ith bit of our ordinal and the I plus first bit of our ordinal, and all you do is XOR those together. Pretty simple. And if you wanted to write it in C or a C-like language, there you go, right? You just XOR it. The caret is the XOR operator for those of you who've never used it. And then we just shift X right by 1, XOR it with itself, and we get the gray code. And what's really nice is if you're counting word operations, it's a constant number of word operations to do that. I'm not going to say exactly how many because it depends on your compiler and your architecture and all that, but we know that it's a constant number of word operations. So now we get to the question that Jessica and I were looking at, which is, what about when n is not a power of 2? Could we just take the first n things of the binary reflected gray code? So here we'll take an example where we want the first 13 numbers, but in gray code order. So I want 0 to 12, because n is 13. So here I've highlighted, can you see that green? Yeah, I guess so. Yeah, here I've highlighted the first 13 numbers of the binary reflected gray code. And this doesn't work, because we get these numbers that we don't want, 13, 14, and 15, and we don't get the numbers that we do want, 8, 9, and 11. So how do we do this? Well, I'm going to tell you in a minute, but first I'm going to confess something, which is that we did figure it out, but boy, did it take us a long time, and we did it all by trial and error, coming up with ideas. They didn't work, but we gained intuition. We come up with another idea. It didn't work. We wrote a lot of code testing stuff out, but eventually we stumbled upon the answer. And it turns out that the solution to getting a sequence of numbers from 0 to n minus 1 with the gray code property is surprisingly simple. Here's how you do it. You take the first n numbers of the binary reflected gray code for the next higher power of 2, just like I showed you, where if I want 13, I would take the first 13 of the code for 16. And you just XOR each of them with the floor of n over 2. That's all you have to do. And it's a constant number of word operations per number. Let me show you an example. So here we're going to start with the same ordinal as before, and it's got the same floor when you divide it by 2. But now we'll look at n equals 13, which is 1101, and we shift that right by 1 bit, so we have 0110. We XOR the whole thing together, so XOR bitwise each of those 3 numbers together, and we get 1000, 3 zeros after the 1, which is 8. All right, so now all we have to do is modify Gray's formula to throw in an XOR of n sub I plus 1. And in code, simple as that. And it's just a constant number of word operations. And amazingly, this works. Now, what I'm going to do is I'm going to prove later a more general thing that works. Here we are looking at what's essentially radix 2. And later on, we'll look at fixed radices that can be any number, at least 2. And I'm going to prove that this works for any radix. 2 happens to just be one of them. But again, we can just look at the idea here. So I've made a little table here of the dense gray codes for n equal 13. And the idea here is when we look at the floor of n over 2, we just look at all the bits that are 1s. Because, you know, when you XOR by a 1, that's just flipping the bit, right? It just changes a 0 to a 1 and a 1 to a 0. If you XOR with a 0, it stays the same. So really, it's just where are the 1s in the floor of n over 2, and those are the bits that we're going to flip, right? And that gives us the dense gray code that you see here. And you can see the decimal equivalence. I don't know how quickly you can read binary, but if you want to scan it and verify that I got all the decimal equivalents right, and indeed that is going to be a permutation of 0 to 12. On the other hand, it's not cyclic, right? When we go from the last number back to the first, lots of bits change, not just 1 bit. So this wasn't cyclic. So Jessica and I were wondering, how can we make this cyclic? Well, we realized very quickly that to be cyclic, a binary gray code must have n be even, right? And it took us just a moment of thought. This was probably the quickest result that we got, and it turned out it was already known. So the idea here is you're going around a cycle, and 1 bit flips every time as you go from number to number if it's a gray code. And every time a bit flips from 0 to 1, well, there better be a flip from 1 to 0 in that bit because you're going to end up where you started. And every time a bit flips 1 to 0, there better be a flip 0 to 1 in that bit because you're ending up where you started. And therefore, the number of 0 to 1 flips equals the number of 1 to 0 flips, and it's 1 flip per number. So that means that the number of flips has to be even, and therefore the length of the cycle has to be even. So we knew already that we didn't have to worry about n being odd. All right, so now here is how we got cyclic binary gray codes. And this is another case where we thought about it for several weeks. And Jessica was going to be away for our spring quarter and summer quarter last year. We were working on it for several weeks during the winter last year. The last day that she was going to be around, I carved out all weekend. Excuse me, not all weekend. I carved out the last Friday, the whole afternoon to work with her. And at 4:30 we figured it out. And then she was gone for 6 months. We wrote this up, and everything that I've shown you so far is in a paper that we created for over 2. Notice I don't have to take a floor here because n is even. So I know n over 2 is an integer. Reflect it. And then append 0 to the top half. In other words, put it on the right-hand side. Now, when we have the dense binary gray code for n over 2, that gives us numbers 0 to n over 2 minus 1. When I append a 0, that's doubling every one of those numbers. So that's going to give us all the even numbers from 0 to n minus 2. And then we're going to append 1 to the bottom half. And that's going to give us all the odd numbers from 1 to n minus 1. And those are all the numbers that we need, and I'm going to show you how that works out. So let's look at it for n equal 10. So here I've shown you the binary reflected gray code, the regular binary reflected gray code, not our dense gray code yet, for n over 2, which is 5, 1, 0, 1. And what I've also done is figured out if I'm making a dense gray code for 5, well, that means I got to take 5 over 2 and take the floor, because I'm going to XOR everything by that, right? So when I take the floor of 5 over 2, I get 2, which is 0, 1, 0. I've highlighted the bits that I'm going to flip. So I get the dense gray code for 5, and there it is, and there are the decimal equivalents. So now what I do is I reflect it. So I've just written it in reverse, and I stick a 0 at the end of the top half, and that gives me the even numbers, 4, 6, 2, 0, 8. I stick a 1 on the bottom half. That gives me the odd in that. And if you look at an integer with a radix R representation, let's say the integer has k digits that we index from k minus 1 being the most significant down to digit 0 being the least significant, it represents the value that you see here. You sum up the ith digit times the radix to the ith power, sum all those up. So a good example, if we're talking about time, where we have a radix of 60 for minutes and seconds, we talk about 23 minutes and 14 seconds. How many seconds is that? 23 times 60 to the 1 power, plus 14 times 60 to the 0 power, that many seconds. So when we are talking about radices other than 2, we need to understand what is the gray code property. So instead of saying that only one bit changes from one number to number, it's one digit changes from one number to number. But we're going to be really strict about this. In fact, there's a property that we're calling strictness, which is not only does one digit change, but that digit that changes by only 1. So let's say we're talking about the radix being 10. If a digit is 7 and it changes, it's got to either go to 6 or 8. Can't go to anything else. And if a digit is 9, it has to go to 8 with strict gray code property. Okay? So in 1984, a fellow named M.C. Eyre published a way to do fixed radix gray codes for what we call full gray codes, where n is actually r to the k. So we're going to list out all the numbers, sort of like in the full binary reflected gray code, where n is a power of 2. So here is our Eyre's method for r equal 3. And first of all, let's look at it when n equals 3. And all you do is you just write out the numbers 0 to r minus 1. Right? That's pretty obvious. All right. And then what we do is we are going to now go up to one more power. Here we're going to go to r squared. In this case, with r being 3, it's going to be 9. And I've just shown you the ordinals, but in radix R notation. And what we're going to do is we're going to take what we had before and we're going to reflect it. And then we're going to copy it and not reflect it. So we're going to alternately reflect and not reflect and not reflect. So you can see in the digits that we've shown so far, they have that nice gray code property. And then to get the next digit, well, we'll have R zeros, and then R ones, and then R twos. Let's go up to n being R cubed. So here I've shown the first 27 numbers in radix 3 notation. And again, we're going to take what we had, we're going to reflect it, and then not reflect it. You can also think of it as we reflect it and then reflect it again, which is the same as not reflecting it. And then we stick zeros in front of the first r squared numbers, and ones, and then twos. And that gives us Eyre's fixed radix gray code for n equal 27 and r equal 3. So notice here that for digit 0, the sequences of length r alternate between ascending sequences and descending sequences. So I've highlighted in both the ordinal part and in the gray code part digit 0. And if we were to number the sequences from 0, the sequences that have even numbers when we number those sequences, the ones that are even are ascending, and the ones that are odd are descending. All right, we're going to take advantage of that. Okay, and if we go to digit 1, here the sequences are length r squared. And again, the even ones are ascending, and the odd ones are descending. For digit 2, which is in this case the leftmost digit, well, there's just one sequence. And it's of length r cubed. So that was Ayer's method, but Ayer did not publish a formula saying how to compute this thing digit by digit. Well, Jessica and I figured that out. It wasn't too hard, as it turns out, once we made this observation about ascending and descending sequences. So here's what we figured out. Fixed radix r, we have the ordinal, which is x, k digits, and we want to find its corresponding gray code, which will also have k digits. We'll call those gk-1 down to g0. And simply, it's just that the ith digit of the gray code is going to be the ith digit of the ordinal if it's in an even sequence. How do you figure out if it's an even sequence? You take the ordinal, divide it by r to the I plus 1, take the floor. And that just tells you. And when that's even, it's in an ascending sequence, so you don't reflect it. When it's odd, it's in a descending sequence, and you reflect it. And to reflect the number, you just subtract that digit xi from r minus 1. Right? So when we're going from, let's see, do I want to do this? No, let me not do that yet. When we're going from, in radix 3, a 0 becomes a 2, a 1 becomes a 1, a 2 becomes a 0. All right, so it helped us to figure out Ayer's gray code digit by digit because we wanted to figure out dense fixed radix gray code. So again, n is less than r to some power. So here's an example where we're going to use the radix 3, but n is 16. It's not 27 now. It's somewhere between r squared and r cubed. All right, so somewhere in the middle. All right, and I've listed out the ordinals in decimal, in binary, well, not in binary, in radix 3, and what we would get in Ayer's gray code, and the decimal equivalents. And just as the binary case, excuse me, this won't work out well. Because we get 16 and 17, which we don't want. And we're missing 9 and 10, which we do want. So what we noticed is when we cut off the sequence, it's in a descending sequence for digit 0, right? When I just look at my green and blue areas here, they look like green and blue. They do look like green and blue. That we're in a descending sequence for digit 0. And we're in a descending sequence for digit 1. We're in an ascending sequence for digit 2, though. All right, so what we figured out is if a digit's cutoff is in a descending sequence, then we want to reflect that digit around radix r, and the intuition is that favors smaller numbers, right? Because you're cutting, when you take a descending sequence and reflect it, it becomes an ascending sequence. So here what we've done is we realized digit 0 cut off in a descending sequence. So we took Ayer's reflected gray code, and we took digit 0 and reflected the entire column for digit 0 around radix 3. So everywhere that we had a 0 in digit 0 of Ayer's code, we have a 2. Everywhere we had a 1, we have a 1. Everywhere that we had a 2, we have a 0. And digit 1 also cut off in a descending sequence. So again, we reflected that. Digit 2 cut off in an ascending sequence, so we don't reflect that. So that is our intuition for what we did. And indeed, when we look at the decimal equivalence that we get here, it's dense. Just happens to be dense. Well, we'll see. There's a proof. All right, so let's look at how we do this digit by digit. So again, we'll look at Ayer's gray code, and we'll call those digits gk-1 down to g0. We're going to form a dense gray code, so we'll call that dk-1 down to d0. So the formula is really just look at the gray code and ask where was the cutoff, right? And the cutoff is you take n and divide it by r to the I plus 1, the length of that sequence. And if that's even, the cutoff was in an ascending sequence, so you don't reflect. And if it was odd, it was in a descending sequence, so you reflect. And this expression, take the floor of n over r to the I plus 1, it tells you which sequence contained that cutoff. Was it an even sequence or an odd sequence? All right, so we've seen the formula for going from ordinal to gray, and we've seen the formula for going from gray to dense. So let's combine them. So what we did was we reflected ordinal digit xi to get Ayres gray code if and only if the floor of x over r to the I plus 1 was odd. And then we reflected Ayres gray code digit g sub I to get the dense fixed radix gray code if and only if the floor of n over r to the I plus 1 was odd. So if both are odd, then essentially you're going to reflect twice, right? You're going to reflect digit xi to get gi, and then you're going to reflect digit gi to get di. You've reflected it twice, which is the same as not reflecting. So we combine the formulas to just ask, what is the parity of x over r to the I plus 1 floor? What is the parity of n over r to the I plus 1 floor? If they have the same parity, then they were either both even or both odd, but in either case you don't reflect. And if they have different parities, one was even, one was odd, you reflected one but not the other. So in the combined formula, you reflect. All right, and amazingly, well, maybe not amazingly, but that was the formula that works. Now, let's go back to binary gray codes. So for radix 2, how does this formula that I've just shown you turn into the formula that I showed you before? D sub I, the ith bit of the dense gray code is x sub I, the ith bit of the ordinal, XORed with the I plus first bit of the ordinal, XORed with the n plus first bit of the ordinal. Well, let's see how this works. When you have a radix 2, and you look at those expressions, what you're really doing is you're dropping the rightmost I plus 1 bits of the two numbers. So what you're going to get is you're going to drop bits 0 through I. So the new rightmost bits are bits I plus 1 of both x and n. Okay. So when we take these expressions, when we ask what's the parity of these numbers, well, when you think about a binary number and you're asking is it even or odd, you're just asking about the rightmost bit. Right? So here we're just saying, all right, let's just take these parities, take their floors mod 2, which is going to be 0 or 1, and it's really just those individual bits. We're just asking about bits x sub I plus 1 and n sub I plus 1. All right, so if those parities are equal, then those bits are equal. And when you XOR bits that are equal together, you get a 0. And when you XOR anything with a 0, you get the anything. So when we look at xi XORed with this other stuff, we just get xi, which is what the formula said, right? The formula from before said that when the parities are equal, di is xi. Okay, and then if they're not the same, then the bits are not the same. And that means that when you XOR those bits together, you're going to get a 1. And when you XOR something with a 1, you flip it, right? And flipping with a 1, well, if we're talking about bits, flipping with a 1 is the same as subtracting from 1. And 1, for radix 2, is the radix minus 1. So we get exactly what we expected. All right, so I came a long way here to tell you about this. So I got to do a proof of something, right? You want to see proof. So let's do a little proof. Little proof. Won't be too bad. So to show that we get a dense gray code, I need to show 3 things. I need to show that all the numbers are unique and that the strict gray code property holds. Those are really easy, and I'm not going to insult your collective intelligence by going through the proofs of those. Those are actually pretty easy. What's more interesting is showing that we don't get numbers out of range. That if the ordinal is less than n, then the dense gray code is less than n. If you put all 3 things together, that's exactly what we wanted to show, right? If all the numbers are unique and they're all in range, I've got to get all the numbers, right? I've got to have a permutation of 0 to n minus 1. And if the gray code property holds, we're great. So let's just see a quick little proof showing that with this double reflection or however we did it, that we're going to have numbers in range. All right, so if we assume that the ordinal is less than n, there's going to be some leftmost digit of x that's less than the corresponding digit of n, right? That's how it works. And it also tells us that if that digit is position j, everything to the left of position j in x and n have to be equal, right? Because I just said it's the leftmost digit that is less, and everything else is going to have to be equal to the left of that. All right, so what that tells us is not only are all the digits to the left of j equal in x and n, but it also says that when I take the floor of those over, when I divide by r to the I plus 1 and take the floor, those are going to be equal for all those positions. For I equal j all the way up through k minus 1, those are going to be equal. All right, and by our formula, that says that those digits of the dense gray code and those digits of the ordinal are going to be equal by the formula that I showed you before for positions j through k minus 1. So therefore, when we look at those positions of the dense gray code and our ordinal x, those are going to be equal. And we assumed that those positions of the ordinal x and n were equal. So therefore, when we look at positions k minus 1 all the way down to j plus 1, they're equal in the dense gray code, the ordinal, and n. And remember, we're trying to show that d is less than n. What about position j? Well, position j, again, d sub j is going to be equal to x sub j by our formula. And by our supposition, that's less than n sub j. So what does that tell us? It tells us that when we look at these numbers, let's look at d and n. Well, in bits k minus 1 down through j plus 1, they're equal. In bit j, d is going to be less than n. So therefore, these numbers are going to work out to be d less than n. It really doesn't matter what happens with the bits to the right of position j. We just don't care about those. All right, so I've given you a proof that we get the right result. So let's move on to mixed radix gray codes. So now instead of a single radix, we have a tuple of radices. We got a whole bunch of radices. So we're going to number those. We're going to index those, k minus 1 down to 0. And now when we talk about an integer with a radix r representation, and the integer is going to be represented the same with k digits, it's going to represent the value that you see there. We're going to sum up the ith digit of x, our ordinal, times the product of all the radices to the right of it. And whenever I tell students that Jessica and I are working on mixed radix, they go, "What's that?" And I'll say to them, "All right, what time is it right now?" And they tell me what time it is. And I say, "All right, how many seconds past midnight is that?" And they realize, oh, that's mixed radix. Because we number the hours with 24 and the minutes and seconds with 60. So in our example here, if we talk about 15 hours, 23 minutes, and 14 seconds, that really means 15 times 60 squared plus 23 times 60 to the 1 plus 14 times 60 to the 0 seconds. All right, so mixed radix, it's not that hard. It may not be obvious, but yeah, if you think about time, it's not that hard. All right, so it turns out to be pretty convenient to denote the product of radices. So we're going to say if we take radices 0 through I, we're going to call that p sub I, the product of radices 0 through I. So p sub I actually has I plus 1 terms or I plus 1 factors in it. So that we can rewrite our representation as really just the sum of xi times p sub I minus 1. All right, and if we think about that, for I equals 0, I minus 1 is minus 1. So we need a p sub minus 1. Well, that's a product with nothing in it, so that's just going to be 1. And if you think about our fixed radix situation, I mean, fixed radix is really just a special case of mixed radix where all the radices just happen to be equal. So for our fixed radix situation where we're so worried about what's r to the I plus 1, well, that's just p sub I, which has the I plus 1 rightmost radices. All right, so it turns out that for dense mixed radix gray codes, It's just the tiniest little change to what I just showed you before. So I'm repeating here the formula for dense fixed radix gray codes. And below is the formula for dense mixed radix gray codes. And the only difference is when we're reflecting, instead of subtracting from the fixed radix R, we subtract the ith digit from the R sub ith radix. And when we're asking what was the floor of x over r to the I plus 1 or n over r to the I plus 1, just change that to x over p sub I or n over p sub I. And that's all you got to do. And the proof is pretty much the same. I won't go through that. So let me just show you an example here. So here I've got mixed radices 3, 2, and 3. So R2 is 3, R1 is 2, R0 is 3. And n is going to be 16, which is less than the product of the radices. So we don't want all the numbers 0 to 17. We want 0 to 15 in mixed radix with the gray code property. So I've shown you here the error-like gray code, how we would do it if we were error. And again, we see the same kind of thing where digit 0 cuts off in a descending sequence. So we're going to reflect around R0. So R0 being 3, we subtract from 3. Digit 1 cuts off in an ascending sequence, so we don't reflect around that. And digit 2 cuts off in an ascending sequence, so we don't reflect around that. And if you look at our dense mixed radix gray code there, you see that the gray code property does hold. We change just one digit from number to number, and the digit that changes is always changing by exactly 1. And when we look at the decimal representations in our mixed radix, it's dense. Okay, so that was just a minor modification. Then Jessica and I started wondering about how can we make these things cyclic. Now we know that not every gray code is going to be cyclic. We can't necessarily make a cyclic gray code for every n, because we've already shown that for radix 2 and n odd, you're out of luck. So we're going to look at a specific situation right now. We're going to look at what we call full mixed radix gray codes, or cyclic mixed radix full gray codes. I can never remember the order that we put all the adjectives. So here we're going to say n is really just the product of all the radices, right? Which is p sub k minus 1, all the radices. And in order to talk about cyclic gray codes for numbers that aren't binary, we really needed to relax the definition a little bit for cyclic gray codes. So instead of the strict property where everything varies by 1, we're going to say it varies by 1 modulo the radix. So now if we are talking about a radix that is 10 and you're at 9 and that's the digit that changes, it can go to 8 or it can go to 0. And 0 can go to either 1 or to 9. So it's this modular ring, which I'm sure you all are familiar with. So here is how we can construct these things. And this is actually a result that Jessica came up with. She and I were in my office, and she came up with this. She saw it before I did. I was so proud of her. And I'll tell you this. I eventually came up with a different way to look at it. And for a couple of weeks, we thought, oh, so there's my way, which is a different construction from Jessica's. And they were both right. Jessica's, you'll see, we have a nice recursive way that we can talk about it. We coded it up. And then after a couple of weeks, I realized, oh, mine doesn't actually work all the time. So I was even more proud of Jessica. All right, so here's the idea. So I'm going to do this for the radices 3, 2, and 3. N will be 18, which is the product of those radices. And what we'll do is we'll start off by just listing out the digits 0 to R0 minus 1, in this case 0 to 2. And for the next digit, I'm going to start by putting a 0 on the left of everything that we already have. And then I'm going to copy each of all the lower digits a number of times, which is R1 minus 1, from bottom to top. So R1 here is 2. So I'm going to copy each of these digits just once from bottom to top, 2, 1, and 0. And then I'm going to lay some 1s in here. So I prepend the 1s in here. Well, having a radix of 2 doesn't show you all that much. So now let's look at what happens when we go to the next radix, which is 3. So again, I'm going to start by putting a 0 to the left of everything that I had. And then I'm going to take the digits that I already had, and I'm going to copy them R2 minus 1 times. R2 is 3, 3 minus 1 is 2. So I'm going to copy each one of these digits that I had 2 times, but I'm going to start at the end and go up. So I take 1, 0, I copy that twice. 1, 1, copy that twice. 1, 2, 0, 2, 0, 1, and 0, 0. And then I'm going to start filling in the top digits. Now I've already filled in all the zeros. I got to fill in some 1s and 2s. So I'll put in a 1 and a 2, and a 2 and a 1, and a 1 and a 2, and a 2 and a 1, a 1 and a 2, and a 2 and a 1. And there we have a cyclic mixed radix full gray code. And you can see it's cyclic when we get to the bottom, 1, 0, 0. We wrap up to the top, 0, 0, 0. So that worked. It could have been that we ended with 2, 0, 0, but that would still be okay because we can go from 2 to 0 in radix 3. So that's pretty nice. And you can see that it is, we've got the decimal equivalents here, and you can see that it is cyclic and it is dense. So that worked out really nicely. So the next question Jessica and I looked at is, well, what about if it's not full? What if n is going to be less than p sub k minus 1? Well, we asked for which radices and which values of n can we even get these cyclic, dense, mixed radix gray codes. So dense, 0 to n minus 1, cyclic, wraps around, and we don't know. But we reduced it to finding a Hamiltonian cycle in an undirected graph. So you have the vertices just being the integers 0 to n minus 1, and you put edges between vertices if they may appear consecutively in the gray code. And you guys know what a Hamiltonian cycle is? It's a cycle in an undirected graph that visits every vertex exactly once. Of course, it starts and ends at the same place. Well, that's what we're looking for here, right? Every vertex would be a number in the gray code, and we want it to be cyclic. So that's great. We've reduced it to an NP-complete problem. Yay! Take something that's easy and make it hard. Well, actually, we don't know if it's easy. But the maybe good news, we're not sure here, is that we know that the Hamiltonian cycle problem is NP-complete for general graphs, but these aren't general graphs. These are graphs with a particular type of structure. So we actually just don't really know. But sometimes it works out beautifully. So when I was preparing this talk, I figured, well, let me try one out. And I tried 3, 2, 3 for the radices, and I tried n equals 16, which in this radix notation is 2, 1, 1. And I sat down with pencil and paper, and it took me a few minutes, but I worked it out. And indeed, this one actually has a Hamiltonian cycle. I was really glad it did, because if it didn't, it was going to take me a long time to figure that out. But this one does. So you can see the graph here, and I'm showing you the edges, and the edges with the red form a Hamiltonian cycle. So for this particular problem, there is a cyclic dense gray code. But as we know from our binary situation, it doesn't always work out. So Jessica, on her own, came up with these two theorems where we can't have a Hamiltonian cycle. So if n has this representation, some digit q, then a bunch of zeros ending with a 1 in whatever mixed radix, if q is either 1 or less than the leftmost radix minus 1, then its graph has no Hamiltonian cycle. And the reason is that that graph has vertices, or at least one vertex, of degree 1. And if there's a vertex with degree 1, right, it's just got one edge, you go in, you can't come out. So it can't have a Hamiltonian cycle that visits every vertex. And then Jess came up with this really cool theorem where she said, all right, if n is odd, and all the radices are even, except for maybe the leftmost one, and the leftmost one is either even or strictly less than that radix, then its graph has no Hamiltonian cycle. And a corollary of that is a cyclic binary gray code must have n be even, what we saw before. Why? Because if all the radices are even and n is odd, we actually fit the conditions of this theorem. All right. So we've gone over a bunch of things, right? Here's the full outline. So this is actually the conclusions. We have seen all these different things in one talk. So there are some open questions. Jessica has graduated, but she wants to keep working on this, so she and I will keep working on this. And we have some questions, which is, for her recursive formula, can we come up with a digit-by-digit representation? We spent one of our working sessions trying to do it, and we couldn't figure it out that day, so we gave up temporarily, but we suspect there's some digit-by-digit formula, or maybe a different algorithm. And then there's this question of, well, when can you get these cyclic mixed radix gray codes? For what values of n, for what values of radices? Jessica has written code to try to find Hamiltonian cycles. Sometimes the code doesn't find one, sometimes it does. We haven't figured out a pattern yet. And then when there is a cycle, suppose we could actually say, that you have a Hamiltonian cycle, if and only if this combination of n and radices, how do we find it? Can we find it quickly? Can we find it in polynomial time? So if this interests you and you want further details, I am pointing you to Jessica's senior honors thesis, which is a Dartmouth College Computer Science Technical Report, number TR2 2017, that's the year, 818. There's a URL there. You can go to our website and just search for it. And that's about all I had to tell you. So thank you. Before we get to the questions, I just wanted to say that I did come a long way to be here, and I know a lot of people came here to see me. So after the official question and answer period is over, I'm happy to stay and answer other questions and talk with people, as long as you can stand me.
Well, thank you for this amazing lecture, and we have time for maybe 3 or 4 questions. Would you like to ask anything?
We have a question here.
Might be a dumb question. We started with binary gray codes. Do we know any other algorithms to construct the gray codes which are cyclic and fulfill all other conditions we would like them to have?
For binary gray codes?
For binary.
Well, so it's actually pretty easy, because you can start with the binary reflected gray code. And suppose you flip every digit in a particular column. Well, that's going to also give you a gray code. And if it started out cyclic, it's going to end up cyclic. So you can flip any column and get another gray code. Or you could permute columns. Right? You could say, all right, take these columns and just move them around. And that's still going to be a gray code. So there are lots of ways to do it. So if you have, let's see, if you have k bits, right, there are k factorial permutations of columns, and then you can flip each one. So that's going to give you, 2 to the k factorial, different ways to do it? Something like that.
Okay, so follow-up question, because I assume that there are other ways, and have you tried these other ways for different radices and different cases which you consider?
We have not tried these other ways. We are just thrilled with what we came up with.
Thank you.
You started with a very convincing example of a turning wheel and so on. That's obvious, that's very useful. But what about other codes? How can they be used?
Yeah, I was afraid of that question. Yeah, I actually don't know of specific applications for gray codes that aren't binary. They're probably out there. Jessica and I just got interested in this stuff in the first place. You know, originally we were looking at these other questions, the FFTs and then the multiplication, and we really just got sidetracked on gray codes. And last summer I wrote to Jessica and said, you've put in so much effort on gray codes, that's maybe what your thesis should be. So that's when we started looking at these other radices. So my defense would be the following. For a long time, people loved number theory because it was considered this pure branch of mathematics that had no applications. Then one night, Ron Rivest drinks a bunch of wine at a Passover Seder, and he's lying on the couch and he figures out RSA. And it turns out number theory has this amazing application that, as Len Edelman said in a video I saw, they realized that the fate of nations could rise and fall with it. So even if I don't know of applications for gray codes other than binary, they may be out there. And it might be that there are some that are already known and I just don't know about them. But you just never know when these applications are going to come up.
This is also my theory. That mathematics is just like a shop. The physicists are coming and buying sometimes from the shop.
Right.
And then they really describe some theory of the universe. Yeah?
That's right.
So
That's right.
at first, this shop must be full of goods to buy.
Very good.
At the start of the presentation, you mentioned that you use the gray codes on Fourier transform stuff.
Yes.
Could you elaborate on that?
Okay, so when you're doing a Fourier transform, if you think about the Cooley-Tukey algorithm, I don't know if you're familiar with that, it's the one that's in our book. Yeah, that one. Strong arms to raise it up above your head. When you look at it bottom up, the very first thing you're doing is bit reversal permutation. And that's actually a bit-defined permutation. You can define that by taking the index of each item, writing it in binary, treating it as a vector, and then multiplying it by a 0-1 matrix. And the multiplication is over GF2. I mentioned that before. GF2, for those who don't know, GF2 is just like regular arithmetic, but it's just got zeros and ones. And multiplication just means logical and, right? 1 and 1 is 1, anything else is 0. And addition is XOR. You can also think of it as just like a regular arithmetic, but you're only keeping the bottom bit. So there's this type of matrix vector multiplication, and that can define a permutation if the matrix itself is invertible. So how do you multiply a matrix by a bunch of vectors? In particular, if we have vectors of length k, there are going to be 2 to the k different values. And how can we multiply matrices and vectors quickly? And what I came up with was a way that if you can pack each column of the matrix into a word, and you can, I mean, these matrices can't be that big, and you pack the vector into a word, you can actually come up with the products in linear time. So the 2 to the k products that you need, you can come up with that in theta 2 to the k time by not treating the vectors in numerical order. Don't do 0, 1, 2, 3, 4 up to 2 to the k minus 1. Do them in gray code order. And the reason is, if one bit changes, you have to figure out, all right, what bit was that? And then you just take the column for that position, and you just are XORing by that. So you just take the previous result, XOR that column in. All right? And then you have to figure out, all right, well, how do I know what bit changed? And, well, that actually isn't that hard. You can just look at what bit changed. And half the time, it's bit 0 that changes. Half the time, of the remaining time, it's bit 1 that changes. Of the remaining time now, half of that, it's bit 2 that changes. When you add all that up, you're looking at just twice the number of bits that you needed. So you can actually do the whole thing in linear time. So that's why I got interested in gray codes in the first place. That and they're cool. But that's why Jessica and I were looking at it, because we were looking at FFTs of non-power of 2 problem sizes. We had to think about gray codes for non-power of 2 sizes. And it was amazing to us that this just never appeared in the literature. You'd think, gray codes have been around since 1953. They're older than me. And they've been known even earlier than that. You'd think somebody would have asked that question, and nobody did. And, there was low-hanging fruit, and we picked it.
Any more questions?
Okay, I have a question about the process of finding the human compounds and how all the codes can be found. So is it always a process of test and learn, and trying to use the mathematics behind it, or can you use some neural networks, artificial intelligence, or is it a waste of time?
Well, we know it's NP complete. So you can put neural networks on it, but if there is no Hamiltonian cycle, I don't know how a neural network is going to figure that out without trying a bunch of unsuccessful attempts. Jessica wrote code that just exhaustively searched. And she ran it on multi-core machines to make it run faster. And I had suggested, well, what she found was that when there was a Hamiltonian cycle, her code found it pretty quickly. So I suggested to her one optimization she could make was, if the code's running for a while and doesn't find one, give up. But of course, that isn't really a proof.
Would anyone like to ask anything else? Don't be shy.
So are you going to write another one book about algorithms or something like that?
Well, I think that's all, and we would really like to thank you for those 3 great days. And of course, really big thank you for everyone who made this happen, to the lecturers, to the students, of course sponsors, also university authorities, and to all of you who came here. And we really hope to see you next year. Thank you.
Maybe right here. It's like our tradition. Because the 4 students' association are organizing this conference, so each one is for one of them, and the 5th one is like for the earthquake.
Maybe here because of this rain. Nie. Mam pytanie. Idziemy na koniec? Nie.